Yes, I'm Chris Lovell. I'm a Dennis Sharma Fellow at the University of Portsmouth. Thank you so much to the organisers for having me to give this review talk today. I'm really jet lagged. I feel like I've been hit by a bus, and not one of the local buses, like a big red double-decker from London kind of bus. So if I stop being coherent, I really apologise for that. So I'm going to talk. Yeah? Okay. How's that? Better?
Oh, yeah, it's better. Forget you have a microphone.
Okay. I'll go for that. So this is meant to be a sort of review talk and a summary of this sort of high redshift simulation space. By necessity, this is going to be a slightly biased view of that, and I will inevitably forget to mention somebody's favorite numerical simulation. So please, I apologize for that now, and please come and speak to me afterwards, if I have. So the kind of key goal, and this isn't necessarily restricted to high redshift galaxy evolution, but the key goal of galaxy evolution modeling is to simulate a representative population of galaxies, resolve all of the relevant physics and down to the required scales that you need to do that, and explore the full range of cosmological and astrophysical parameters that might impact any of the observables that you care about. So in order to do this, we need really, really large volumes to capture the range of environments that we see in the real universe, high resolution, so that's in terms of spatial, time, and mass, including all of the required physics, and also, ideally, large suites of simulations where these parameters are changed and we can see the impact on the observables. Now, clearly, it's not computationally feasible to achieve all of these simultaneously, and so compromises have to be made along sort of any one of these three axes of merit. So this is the very sophisticated visualization I came up with for this. So we have large volumes at the top, sophisticated models / high resolution at the bottom left, and then large suites of simulations. So if you want large volumes, you typically have to sacrifice some of the fidelity and typically run a single simulation. If you want sophisticated models, you have to sacrifice the volume and typically rely on a single simulation. And if you want a large suite of simulations, then you typically have to sacrifice the volume and also the fidelity as well. Now, of course, when we compare models to observations, there's different places we can do this, depending on what sort of comparisons we wish to make. Where's the other look? Okay, great. So we typically go from, we wish to compare our physical models here on the left-hand side to our observations on the right, and depending on how we do this, there's different places we can do it. So going along the bottom here is typically what your observers would be doing, right? So you identify some sources in your observations, you perform SED fitting on those sources to get some physical properties, and then perform some phenomenological modeling to understand the physics behind those. On the simulation side, we go the other way around, right? We take some physical laws, we run numerical simulations to obtain fields describing the density of matter, maybe like dark matter or gas. We then typically run structure-finding methods to find the physical properties of individual objects. And then, if we're feeling really brave, then we do some SED modeling to mock up the observable properties of those galaxies. But typically, we're comparing sort of here, right? We're comparing stellar mass functions, the star-forming main sequence. Sometimes we're comparing here. And if we wanted to do something like, compared to line intensity mapping observations, we might need to do this whole step here directly to the observations. But it depends, there's no right way of doing this. There's value in basically doing this comparison in these different spaces. But often we tend to just do this one. So with that in mind, we're going to move on to kind of go through sort of these three main sort of flavors, I guess, of simulation. And to sort of motivate each one, I'm going to go over sort of these three key problems, I guess, that we've seen over the last couple of years that have already been described in detail this morning. This is the overabundance of massive galaxies at high redshift, little red dots, and this sort of UV upturn, which is maybe confusingly named a little bit. So large volume. To sort of motivate this, I was going to highlight these sort of overmassive galaxies. So this was the sort of state of play in early 2022, the Evo Labe results, sort of somewhat higher than what we might expect from even our lambda CDM cosmology. And I think everybody's aware of the fact that there were calibration issues there, and we've improved our modeling of these galaxies to get better stellar mass estimates that have reduced that tension somewhat. I also just wanted to highlight that there was also a lot of early papers that sort of compared two models in this space, but didn't necessarily compare and take into account the volume of these simulations. So you'll notice here in this is Steve Finkelstein's paper, you have a huge number of models here, but some of these cover very, very different ranges of volume. So from Simba and Fisan, which are on the order of tens of megaparsecs, up to some of these sort of semi-empirical models and flares, which goes up to sort of gigaparsec volumes. And you saw, so this was a paper from Hasselbauer where they compared to the sort of most massive object from the Eagle and TNG simulations, showed that they weren't reproducing these objects, and therefore concluded that, that these things were in tension in some sense. And this is I'm not picking on anybody here, so I'm not going to attribute this quote. But there were a lot of statements like this, right, where galaxy formation models need to address the existence of these large objects. And that's, absolutely fine. And I think, in some sense, those early JWST results, given the areas of these surveys, relatively small, relatively shallow, that I think, it was kind of fair, I guess, to not expect there to be a lot of these massive objects, and also expect that the kind of volumes probed are actually going to be quite low. So I made this sort of figure of merit to try and maybe squash that a little bit. So what this is showing is the volume probed between some redshift limits, so some delta Z, and it basically shows the area covered within that delta Z in co-moving megaparsecs. So you can see here for something like JADES and Cosmos Web, for example, you need a volume of at least sort of 100 to 200 megaparsecs cubed in order to probe a sort of delta Z between 9.5 and 10.5, for example, at this sort of redshift. So these are quite big volumes, actually. And that's actually just the very bare minimum volume that you need, right? So I went and took a look at the sort of TNG suite of simulations. So the nice thing with TNG, they have a 50 megaparsec, 100 megaparsec, 300 megaparsec box. And you can kind of subdivide those boxes to see what the sort of impact is of cosmic variance on the scales of these slightly smaller boxes, right? So in terms of the 300 megaparsec box, you can divide that into sort of 27 subdivisions and look at the most massive halo in those sub-boxes and compare it to what you get for the 100 megaparsec one. So this is the most massive halo in the 300 megaparsec. This is the distribution of most massive halos in the 100 megaparsec subvolumes. And this star here is the most massive in the 100 megaparsec. This is at redshift 0. But you can see that there's almost an order of magnitude scatter here. So even at that minimum volume that you need to compare to something like JADES or to Cosmos Web of like 1 to 200 megaparsecs, you're still going to be missing a lot of these very, very massive objects in terms of cosmic variance on that same scale. And this is the situation at redshift 10. So not quite as drastic, but there's still objects that are sort of 0.3 dex higher in halo mass here compared to this sort of 300 megaparsec scale. So what does the state of play look like in the sort of large volume regime? So it's sort of nicely summarized here by this Risa Wexler review paper on the galaxy halo connection. But essentially, we're looking more from these sort of empirical forward models all the way up to hydro simulations. So on the semi-empirical model side, we have the Jaguar empirical models, sort of this mock image here at the bottom showing some nice predictions here, even taking into account empirical morphologies, and then things like Universe, Machine, and Trinity, which I'm sure we're going to hear more about the rest of this week as well from Peter and Helen. Going to slightly more sophistication, semi-analytic models. So there's a number of sort of well-established semi-analytic models from the last 10 to 15 years, such as Galaxies, Galform, and SC-SAM, that have been applied to this sort of high redshift regime, in particular Aaron's work, which you all just heard about, linking this to sort of more sophisticated models for the halo mass function and merger trees, and then sort of dedicated models for semi-analytic models at high redshift. So this is Delphi and Astreas, for example. And the nice thing with all of these models is that we can go to these very large volume regimes and create sort of mock light cones and really test the impact of things like cosmic variance in this large volume regime. And we can run them down to redshift 0. So we can calibrate them and check that they look reasonably good. Going into the hydrodynamic simulations now, so increased sophistication, there's a number of, again, sort of classic or standard hydro sims from the last 10 years. Eagle, Illustrious TNG, Simba, Horizon AGN, New Horizon, and Firebox as well recently, which all take these periodic hydro simulations that have been sort of tested, often hopefully down to lower redshift, maybe not Firebox, and probe galaxy formation on scales of approximately 100 co-moving megaparsecs cubed. But I wanted to highlight two sort of alternative approaches to this. So this is the blue tides and Astrid simulations. So these take much, much larger volumes. So blue tides is a 400 megaparsec H inverse box on the side, and Astrid is about 250 megaparsecs. And they run these at the same sort of resolution as these sort of flagship models at the top here, and essentially study galaxy formation in this very large volume regime at high redshift. And you're able to study things like the clustering of matter, massive protoclusters, etc. The disadvantage with this is that you can only run them down to reasonably high redshifts. So blue tides, I think, got stuck at redshift 6.5, and Astrid got down to redshift 3. I think stuck is actually the right word for that. So they tried to get to 6, but yeah. Now, there are other simulations as well in the hydro space on the large volume regime, but not necessarily geared towards high redshift, things like Flamingo or Millennium TNG, that have been used to study this large volume regime as well and compare the predictions for massive objects. Now, another thing you can do is zooms, and I put a question mark there because you might think, why are you saying zooms when we're talking about the large volume regime? What we can do is we can do zooms of different environments and then combine these together to mimic much larger volumes. And this provides a nice advantage in the sense that you can get much more detailed predictions for low mass objects and high resolution. And there's some examples of this are the first light simulations, the Fire and Fire 2 simulations, which did individual zooms of sort of Milky Way-like galaxies, but then used them combined with the halo mass function to reproduce distribution functions. And then here's the bias. They've got flares. So this is a project I worked on the last few years where we combined sort of 40 zoom simulations of different regions from a 3.2 gigaparsec box. So this is this kind of thing you can do. So this is the original Eagle UV luminosity function at redshift 6 compared to some of these sort of typical survey volumes and areas. So we were able to probe with Eagle down to this sort of faint end of the UV luminosity function, but not necessarily the bright end probed by some of the wider surveys. And when we do it with flares, we can now get into that regime. The downsides being that we can't actually measure some of these clustering statistics quite as simply. We have to make some assumptions about the mapping to halos. And how do we also account for the topology of reionization on large scales and incorporate this into the models? Okay, so that was large volume. We're now moving into the sort of more sophisticated models, high resolution regime. And the example I'm going to give for this is little red dots. Right? So we've already heard an awful lot about these, about their incredibly small sizes, whether they contain potentially AGN, whether those AGN are actually super Eddington accreting supermassive black holes. Oops. The fact that these have incredibly small, dense sizes means that we really need these high-resolution, sophisticated models to understand their formation mechanisms properly, right? With the hydro simulations I showed just previously, we don't really have the spatial nor the mass resolution to resolve these objects sufficiently. never mind the actual details of the AGN accretion mechanism. So what does the state of play look like in this regime? So we have periodic volumes. So these are typically radiation hydrodynamic simulations, sometimes including the effect of magnetic fields. They include, some of them include a multi-phase interstellar medium, whether that incorporates a sort of equation of state floor or not. Some of them include the effects of cosmic rays, the impact of population-free birth, direct collapse black holes, you name it, right? But I guess the two I'm going to focus on here are Thesan and Sphinx. So Thesan does have this equation of state floor, but does actually have a live dust model, which sort of sets it apart from some of these other sort of high-resolution periodic simulations. And it's able to, reach volumes of approximately 100 megaparsecs, only down to relatively high redshift, but is able to produce realistic populations of galaxies in this sort of regime. And then Sphinx, which actually does fully simulate this sort of multi-phase ISM, but only reaches sort of volumes of 20 to 30 megaparsecs. And then, there's an awful lot of other simulations in this space as well. If you want to go to even higher resolution in terms of spatial and also include extra physics, we can go to zoom simulations, but now in this very high resolution regime. So again, Sierra, we're going to hear more about later this week, Obelisk as well, and Thesan Zoom, which I think we heard a little bit about earlier in the program. It's not been published yet, but it seems quite an exciting extension. There's also an awful lot of work that's been done on sort of population-free and direct collapse black hole populations that I don't really have time to go into in a huge amount of detail, but again, I'm sure we'll hear a lot more about this week. So these are just the Sierra simulations here, showing some of these objects. So a selection of, I think, 100 zooms. Now, I wanted to highlight some novel approaches now to sort of overcome some of the limitations of these very high-resolution simulations. One of these is AI-assisted super-resolution simulations, so taking much more detailed simulations run with the same initial conditions and essentially learning the relationship between those simulations on different scales. And that essentially allows you then to achieve much higher resolution, much cheaper. So these are leveraging some advances in sort of 3D convolutional neural networks. And then also the super zooms. So this is a combination of the Fire and Starforge models. That essentially allows you to go from sort of AU scales around supermassive black holes out to a fully cosmological environment, taking into account all of the boundary conditions between these different regimes. So this is work led by Phil Hopkins. And there's the AI assisted. So finally, I just wanted to touch on simulation suites. Now, the example I give of this is this UV upturn that's been talked a little bit about already. There's a huge number of different models that have been proposed to explain this upturn, many of them sort of relying on increased star formation efficiency and halos at these high redshifts. One of the examples being the feedback-free starbursts, Decalcel, and reduced dust attenuation, or increasing the mass-to-light ratio using a top-heavy IMF or more stochastic star formation. Now, what would be nice is if we could run models with various, versions of these different models, but also being able to modify all of these parameters self-consistently from first principles. So things like how top-heavy is the IMF, right? Various parameters in this feedback-free starburst model, and run large suites of these to really understand the impact of those assumptions and be able to compare the models more effectively. Now, this is a bit of a sad slide, but essentially these sort of things don't really exist at high redshift. There's some examples of this with Croc. Now, obviously, all simulations do some sort of resolution tests, and they do some sort of exploration of the various different parameters. But what I'm trying to get at here is something more akin to what we see with camels. So this is not a high redshift project. This is a project that is attempting to look at in a more systematic way the impact of cosmological and astrophysical parameters on the predictions. So in the first instance of this, they varied things like omega matter and sigma 8 on the cosmology side, and then these various parameters controlling the strength of supernovae and AGN feedback. And they also run this with lots and lots of different models. So in the current, I think, catalog, there's about 142 million objects, galaxies, halos. And there's also a number of other projects that take this approach as well. So things like Antilles and Flamingo have used this for calibration, and also Quixote on the more the cosmology side. So what would be nice is if we could take these sort of things and apply, the same approach to high redshift. And I really want to highlight this paper from Chustakov et al. That does this in a really nice way. So they take advantage of these new approaches to inference called simulation-based inference. So these are approaches that basically really leverage everything we do in the numerical simulation space and use it to learn, more quickly and more precisely some of these fundamental parameters that we care about. So in this paper, they take the Sphinx simulation combined with this LTU ILI pipeline, which is a mouthful, but essentially this is a pipeline for doing simulation-based inference. They then generate 13,000 mock line-of-sight observations of the photometry from these galaxies and predict the escaped ionizing luminosity. By using this pipeline, they can then apply it to JADES and create these predictions, but using the full details of the Sphinx model. So these incredibly complex star formation and metal enrichment histories that you get in Sphinx, compared to something like bagpipes, for example, where you have to assume much more simplified parametric forms for those. And one of the other advantages of doing this is that you can do what's called amortized inference, which essentially means that you don't have to do any additional sampling to get posteriors on your predictions. So they did this for, I think, 5,000 JADES galaxies, and they basically applied it and got results back in less than a minute, rather than of order that for every single galaxy if you're using something like bagpipes. So this is like some of the advantages you can get when you're able to run these large suites of simulations and apply these sorts of methods. One of the other things I really wanted to highlight was emulation. So there's a lot of new methods now for emulating some of the more expensive aspects of these sort of detailed simulations, and essentially allow us to create these large suites that we can then either incorporate on the fly or use in post-processing for generating observables. So this is one I just wanted to highlight from Q, from UGI et al. Essentially what they did is they did a PCA decomposition of a whole grid of cloudy models. And they did this, with a relatively simple parameterization of the ionizing spectrum, but they also varied the metallicity on these metallicity ratios, the gas density, and the total ionizing photon budget, and built this giant emulator that can actually produce this line continuum and line emission reasonably accurately. And so the power of this then becomes if you can use this within your simulation to actually predict some of these properties on the fly, this makes things a lot cheaper. So this is kind of what the space looks like. It looks a bit empty over here, but hopefully we can fill that out soon. And ultimately, it'd be really nice if we can get something that sort of sits in the middle here, whether that's possible or not. But using some of these sort of more novel techniques that I sort of highlighted already. And I just wanted to, again, highlight this sort of Santa Barbara high-Z comparison project that's sort of started, I think, at the program recently, that's hopefully going to bring together a lot of these models and do a more thorough comparison of their predictions. So I'll finish there. Thank you very much.
Okay, questions for Chris? Sorry.
I can ask a question?
Yeah.
So I really appreciated your talk. It was really, really good and comprehensive. So something that I keep on wondering about, so if you have a large volume simulation compared to a small simulation, I'm more into small simulation generally, the fact that you're missing the star formation history, so if you're at lower resolution, say, 10 to the 6 solar masses for a particle, you are missing the star formation history that happened before you resolve. So what do you feel is happening when we compare different types of simulations to these high-redshift galaxies that definitely had a complex life already when we see them?
Yeah, so there was a nice paper from Josh Borrow who did some work with the THESAN simulations. So these are the high-resolution periodic boxes. Approximately, I think the highest resolution ones they were looking at boxes about 50 megaparsecs inside. One of the nice things they showed actually was that at the high mass end, despite having these much more sophisticated, much more extended star formation histories, the actual resulting galaxy properties, once they grew to a certain size, were kind of similar. Now that might be model dependent, right? But it seems to show that once you on a mass doubling or mass quadrupling time, that a lot of that early star formation history does actually get sort of wiped out in some sense. So I think we can trust some of these slightly lower resolution simulations in that regime. There's obviously limits to that, but yeah.
Okay. Sun-Myun, did I see your hand before? Yeah, go ahead. Yeah, thanks, Marta.
So can I ask, so the AI stuff, so you show in the later slide, and so maybe using AI, so maybe you connect simulation with observational property, and so could you explain what kind of simulation is?
Are you talking about the simulation-based inference? Yeah. So essentially with any sort of inference approach, what you're trying to learn is the relationship between some parameters and some data, right? And so what simulation-based inference does is it provides a framework for doing that leverages advances in sort of deep learning and neural density estimation to actually learn that sort of posterior space more effectively. So what essentially they've done here is you create this huge mock library of these line of sight observations, varying different parameters in your forward model, throw it at LTU ILI, and it learns that mapping for that in that posterior space, and then you can provide it, obviously matched photometry here in JADES, and it will provide you the predictions on the posteriors. There's different versions of this as well, so this is neural posterior estimation that directly learns that posterior. There's also neural likelihood estimation that learns this sort of non-parametric likelihood directly. Yeah, that's sort of the idea, I think.
I'm not sure if people know what LTU ILI stands for. You might want to explain that.
Implicit likelihood inference. So there's a few different ones here. Yeah, so that was LTU ILI is better than that, but yeah. There's a few different words for this simulation-based inference. There's, implicit likelihood inference is another word that's used to describe it. There's some more details in this Matt Ho's paper that describes some of the background to simulation-based inference. So I think, yeah, if you're interested, I'd recommend taking a look at that.
Okay, other questions? Priya?
Thanks for comprehensive walkthrough through the zoo of simulations. I was curious, but all these simulations pretty much use the same prescription for black hole accretion, even though for feedback there is some variation, right?
Depends on the scales, right? But yeah, there's a lot more diversity in the feedback prescriptions for sure. But how you get that mass relatively close, I guess there's more diversity there.
Pretty much they all have anything that crosses the boundary radius essentially is assumed to be accreted, right?
Yeah, agreed. I think there's, now a lot more
except for
interest.
some of the fire simulations that are using the gravitational torque model. And Simba also has a gravitational torque model.
So they have multiple feeding modes, okay.
So just those two that I'm aware of. Again, there's probably others that, we're not aware of. But yeah. Other questions? Yeah.
Hi. I'm curious about the comparison project you mentioned. Is the goal there to understand how the different simulations are different in their predictions, or to assess how different the codes are in kind of controlled tests where they should give the same answer in principle?
I mean, I've just turned up yesterday, and I think this is now an ongoing project that I'm sure Rachel can talk in more detail about.
So I'm thinking of actually showing a slide on this during one of the lightning talk sessions. But the initial goal is to just compare the published results of a bunch of different simulations and try to understand why they're different. Of course, that may lead us down, the path towards more controlled experiments and comparisons. But for now, we just wanted to look at the published models. Other questions for Chris? Can you go back to your last slide? I thought it just might be interesting to discuss, and maybe other people in the room also have thoughts about this, how we can fill out that part of your diagram, which I think is where we all want to go. I mean, you alluded to using machine learning emulators, and I don't know, do you have other thoughts about how we can?
Yeah, maybe didn't emphasize that part of the motivation for this part of the diagram is to enable those machine learning methods, right? So we need these large training sets in order to do this. So camels was one example. This was specifically designed to provide these training sets that could be leveraged by machine learning approaches. And yeah, I think with the Chustakov paper, it showed a nice example of that in this high redshift regime with some really nice advantages over typical SED fitting approaches, and able to leverage all of these simulations that we're putting a huge amount of effort into directly in that sort of inference SED comparison space. Now, I guess, yeah, an interesting question would be which side of this you would care about most? Is it suites of large simulations, or is it suites of more sophisticated high-resolution simulations? And obviously, depending on your question, there'll be differences there.
Yeah, thank you. Any other comments or questions? Briant?
I was just going to comment in the lower right-hand corner, one thing our group has been working on is using Choya simulations, which are limited in spatial resolution. They're fixed grid, but we can run thousands of simulations, and trying to use machine learning methods to deal with the fact that we can't resolve the detailed structure of individual galaxies, but we can capture large volumes and do large parameter studies. So still be a while probably, but it's something that we're making some progress on.
Yeah, thanks for reminding me that I forgot one simulation suite, and it was one of the organizers. So yeah, that was good. Good work.
Peter. Well, go ahead, Marta.
Yeah, so I guess one sticking point with the bottom right corner is funding. And so how do you justify asking for funding to do a simulation suite and all the analysis that comes with it? And I guess that's more of a question for the community. Sort of how do we talk about this to get funding to do it? How do we build enough interest to say, oh yeah, we need a simulation suite as opposed to one big new model?
I think that's a great question, and it has two parts, right? So you need the funding to pay the people to do the work, and you also need the computing time, which is going to be quite substantial. And I agree. I think it's often not recognized how important it is to have these variations of parameters and large suites so that you can explore that.
Yeah, and I think, yeah, like, if anything, the compute is cheaper these days than the storage. So this does raise other issues in terms of those storage requirements. But yeah, just got to sell it, I guess, in terms of the machine learning advantages there. Yeah.
Any last questions? If not, let's thank Chris again.